Hello everyone. So during my masters, I modeled a Bismuthene nanoribbon-based topological insulator field effect transistor based on density functional theory and non-equilibrium Green's function formalism. So in this video tutorial, first of all, I will describe about the theoretical aspect and the simulation methodology. And in the upcoming videos, I will describe the input files. And I will also share my input files in the description box below. Any of you can use those codes for your own research. So let's get started. So during my masters, I basically choose bismuth triple one, which is a bilayer of bismuth, uh, and it has a very large inverted band gap. For that reason, I choose bismuth specifically. So the main motivation. So So the main motivation of choosing bismuth because of its large inverted band gap, and moreover, quantum spin-Hall insulators as a whole have topologically protected resistors. Moreover, they exhibit robust operation at low temperatures. On the contrary, conventional semiconductors have several drawbacks. For example, there might be scattering from defects and phonons, which results in high dissipation electrical noise. And as conventional semiconductors works on diffusion mechanism, and for diffusion mechanism we need temperature. So at cryogenic temperature, that process doesn't work so well. So that's another drawbacks for conventional semiconductors like silicon, gallium arsenide, or other materials. So for simulating a Bismuthene nanoribbon topological insulator field effect transistor, I followed this methodology. And this is a standard methodology. This methodology can be used to simulate any material-based system, specifically 2D materials. So first of all, I did DFT calculation using quantum espresso. As I have already mentioned earlier, that I will I will share my codes with all of you, so that anyone can use those codes. First of all, I did DFT calculation using quantum espresso. So in DFT, basically quantum equations is solved, which is this Schrodinger-like equation. And here this external potential corresponds to the ionic potential, and then we have the classical electrostatic repulsion potential, which is called the Hartree potential, and then all the non-classical electrostatic repulsion interaction is modeled by using this exchange correlation functional. So if any of you have experience with DFT calculation, you know that this exchange correlation functional can be modeled by various ways. For example, by using generalized gradient approximation, or by using local density approximation, or using hybrid functional. So by solving this equation, we get a block type solution. So psi nk equals to the power ik dot r un car. Now, this block wave functions are not localized in position space. They are localized in momentum space, but they are delocalized in position space. However, for building tight binding Hamiltonian, we need localized orbitals. just like atomic orbitals. For that purpose, I used 190 package of quantum espresso to transform this extended block states to the maximally localized one-year function. And after getting the maximally localized one-year function, the tight binding Hamiltonian is generated. So after getting the tight binding Hamiltonian, then I have used the non-equilibrium Green's function formalism in MATLAB to simulate the transport characteristic of my proposed device. So first of all, the Green's function is calculated by using this formula, and then current is calculated by using Landauer-Buttiker formula. So now let's talk about the crystal structure of bismuth triple one bilayer. So bismuth triple one has a bipartite honeycomb lattice. So the unit cell is hexagonal, and in a unit cell, so not hexagonal, but just like graphene. So unit cell is hexagonal, but we can define a lot smaller unit cell which will only consist of 2 atoms. We are designating those 2 atoms by sublattices A and B, and there are some buckling height between those 2 sublattices. And the buckling height between A and B sublattices is around 1.71 angstrom. And the lattice constant for bismuth triple one bilayer is around 4.34 angstrom, and the nearest neighbor bond angles are approximately 91 degrees. Now, for my simulation, I took the crystal data from materials cloud 2D material database. So if you go to materials cloud 2D quantum spinel insulator database, and if you search for bismuth triple one, you will get all the information. So I will talk about more when I will talk about the input file that I have created to simulate all the electronic properties and topological properties for bismuth triple one. So now let's talk about the electronic band structure for bismuth triple one. So bismuth triple one is a quantum spinel insulator. So there will be a band inversion at the gamma point of the Brillouin zone. So as you can see that this is the band structure for bismuth triple one with spinor bit coupling. And with spinor bit coupling, the conduction band minima is predominantly composed of the bismuth pxy orbitals, whereas the valence band maxima is predominantly composed of the bismuth pz orbital. However, if we do not incorporate spinor bit coupling into our calculation, then we will get the band structure for trivial material. So in that case, the valence band maxima is predominantly composed of the bismuth px orbitals, and conduction band minima is predominantly composed of the bismuth pz orbital. So there is an indirect band gap of 0.55 electron volt at the gamma point of the Brillouin zone. And I have also calculated the band structure by using hybrid pseudopotential. And as you have already known that the PB pseudopotential generally underestimates the band gap. And for the case of bismuth triple one, it underestimates by approximately 0.04 electron volt. So now I will going to talk about some important symmetry that is really significant for the analysis of Bismuthene nanoribbon-based topological insulator field effect transistor. The first one is inversion symmetry. So inversion symmetry signifies a system where the system is invariant under a point reflection. And if for a system there is inversion symmetry, then the wave function occurs in even and odd order. So if now now there is a operator uh, associated with inversion symmetry, which is called Pareto operator. And if Pareto operator P operates on a wave function psi, and we get the same wave function, then we will say that there is even parity for which the eigenvalue is +1. On the other hand, if we get negative of psi, we will say that we now have odd parity with eigenvalue of -1. Now, the most important aspect that we can see in band structure, that if in a system there is inversion symmetry, then the then the energy of up spin electron at -k is equals to energy of up spin electron at k. So bands are symmetric with respect to the uh, high symmetry points, for example, gamma points. So here I have also shown the inversion symmetry for the case of an infinite potential well. So as you can see that with respect to the oil center, this infinite potential well has inversion symmetry because the potential is infinity at L/2 and also is infinity at -L/2. As a result, the wave function comes in even and odd order. So the first wave function is even, the second is odd, the third is even, etc. And another important symmetry that will be significant for in our analysis of Bismuthene nanoribbon topological insulator field effect transistor is time reversal symmetry. So we will say that a physical system is time reversal symmetric if it follows this expression. That means if we operate time operator T, the Hamiltonian of the system remains invariant. So the consequence of time reversal symmetry on band structure is that the down spin electron at -k is equals to the up spin electron at k. So, and in crystals, if both time reversal and inversion symmetry persists, then the band becomes doubly degenerate. So, for Bismuth 111, both time reversal and inversion symmetry exist. As a result, the bands are doubly degenerate. So now I will going to talk about topological invariant, which is really important for understanding the physics. So a topological invariant is a quantity that stays constant under smooth deformation of a system. So here we can see that this is a mug which has one hole, and if we continuously deform this into a donut, that one hole still persists. So that hole is a topological invariant, which is called genus. And although we transform this system to a coffee mug to a donut, that property hasn't changed. So we can say that a coffee mug and a donut are topological invariant. Now how we can define the topological invariant of a crystal? Now the answer lies in the band structure of the solid. Now we know that due to periodicity of the lattice, the wave function of a crystal follows the Bloch wave function. That means that the Bloch wave function sin of k is equals to the e to the power I k dot r un k r, where e to the power I k dot r is a plane wave part and un k r is a term which is periodic due to the periodic nature of the crystal. Now, the periodicity of the Bloch Hamiltonian determines the topological invariant. So now let's talk about how we can calculate this topological invariant. So if we took the Fourier transform of real space Hamiltonian, we will get the Bloch Hamiltonian H of k. and if we solve the Schrodinger equation for Bloch Hamiltonian, we will get the Bloch bundle UNK and energy eigenvalue U of k. Now this U of k gives us the energy band structure, and the evaluation of Bloch bundle UNK, and from the evaluation of Bloch bundle UNK, we can calculate the topological invariant. First of all, we can define the Berry connection, which is analogous to the vector magnetic potential. So if we use this formula, we can calculate the Berry connection, and by taking the curl of Berry connection, we can get the Berry curvature, which is analogous to the magnetic flux density. And if we take the surface integral of Berry curvature, we will get the Chern number. So this Chern number defines the topological invariant of a system. So if a material has non-zero Chern number, then we can say that material is a quantum anomalous or insulator. For that case, Chern number is non-zero. Time reversal symmetry is broken. For that case, the edge states have chirality. Moreover, Hall voltage present without the magnetic field. However, if a material has zero Chern number, we have to calculate the Z2 index for determine whether that material is a quantum spinel insulator or a trivial insulator. Okay, so if a material has Z2 index equals to 1, then we can say that that material is a quantum spinel insulator which have zero Chern number. But in that case, the time reversal symmetry is preserved. Edge states are helical. That means that up and down spin electron uses opposite edges to travel through the material. However, in this case, the Hall voltage is absent without the magnetic field. So how can we calculate the Z2 index of a material? Z2 index can be calculated by various methods. For example, by using Foucault formula. I haven't included that here. And if spin is conserved, it can be calculated by using the Chern number. So we have to calculate the Chern number for up and down spin electron, and then we have to use this formula to calculate the Z2 index. And the most easiest way to calculate the Z2 index by evaluation of Wiener charge center. So I have used the Wiener charge center evaluation method to validate that bismuth triple one is indeed a topological insulator. For that purpose, I used the Wiener tool package. I have used Wiener tool to get this data. And so I have plotted the evaluation of Wiener charge center with respect to the momentum number k, wave number k. Now the method is, if the largest gap, so this black circles represent the Wiener charge centers, evaluation of Wiener charge centers, and this red dotted line represents the maximum gap between Wiener charge centers. Now, according to David Vanderbilt, according to one of the papers from David Vanderbilt, if this red dotted line intersects the Wiener charge center line an odd number of times, then the system is a quantum spinel insulator. And if it intersects the Wiener charge center line an even number of times, then the system is a trivial insulator. So as you can see that for bismuth triple one, this red dotted line intersects the Wiener charge center line 5 times. So we will get the Z2 index 5 mod 2 equals to 1. So our system is topologically non-trivial. Now, if we want to build a transistor, we need to induce a topological phase transition. For that purpose, I have also analyzed the impact of staggered sublattice potential and how we can utilize this to induce a topological phase transition. So before going into the detail, let's talk about a very simple system. For example, a 2-atom per unit cell system, the Hamiltonian can be written as this. So initially, there shouldn't be this term. So initially, we are assuming that the on-site potential is 0, and this is the hopping term. So a staggered sublattice potential means that we need to apply different voltages to two different sublattices. So for example, in a system, we apply del electron volt staggered sublattice potential. So it means that we have to apply del by 2 electron volt to one sublattice and minus del by 2 electron volt to another sublattice. So what will happen? That our energy gap will increase theoretically for any material, for example, graphene or silicon or any material. However, for bismuth triple one, there is an inverted band gap. That means valence band is in a, so the energy of valence band is greater than the energy of conduction band. So if we apply a staggered sublattice potential into a quantum spinel insulator, the energy gap will get reduced rather than increased. Because normally, if we apply staggered sublattice potential, it will decouple conduction and valence band. So conduction band and valence band, the distance between conduction and valence band will increases. But as there is a band inversion, as a result, the conduction and valence band, so conduction band will go upper and valence band will go down. So as a result, the inverted band gap will decrease. And we have observed that at around 1.77 electron volt staggered sublattice potential, the system exhibits a Dirac metal phase. And if we increase the strength of a staggered sublattice potential further, then our system becomes a trivial insulator with Z2 index becomes 0. So this is an important finding because we can induce a staggered sublattice potential by applying an electric field. And in our designed structure, we will apply an electric field, perpendicular electric field, to intentionally break this inversion symmetry. So here we have also showed the impact of staggered sublattice potential on Z2 index. So for 0 staggered sublattice potential, the Z2 index is 0. This red dotted curve intersects the Wiener-Sachs center evolution curve an odd number of times. However, if we apply a substantially high staggered sublattice potential of 2.5 electron volt, this red dotted line doesn't intersect any of the Wiener-Sachs center curves. So that results in Z equals to 0. We have also showed the topological phase transition by using the electronic banded structure for bismuth triple one. So as you have already mentioned that for pristine bismuth triple one, there is both time reversal and inversion symmetry. So the bands are doubly degenerate. However, if we apply a staggered sublattice potential, it breaks the inversion symmetry. As a result, the bands become non-degenerate. And at around 1.77 electron volt staggered sublattice potential, the band gap closes. And if we further increase the strength of the SSP, then band reopens. And as you can see that the initially the conduction band minima is predominantly composed of the bismuth PXY states, and valence band maxima is predominantly composed of the bismuth PZ states. which resembles the orbital contribution for bismuth triplet with SOC. However, with staggered sublattice potential value of greater than 1.77 electron volt, the orbital contribution reverses. So in this case, the conduction band minima is now predominantly composed of the bismuth pz orbital, and valence band maxima is now predominantly composed of the bismuth px orbital, which is analogous to the orbital projected band structure for bismuth triple without spin orbit coupling. So now let's talk about the how non-trivial edge states appear in so now let's talk about how non-trivial edge states appear in a quantum spinel insulator. So at the interface between two trivial material, say silicon, or say graphene and say graphene and hexagonal boron nitride. So graphene nanoribbon, say 5 ampere graphene nanoribbon, it has a finite band gap, and hexagonal boron nitride, it has also a finite band gap. But as both two materials are topologically trivial, at the interface between those two materials, the conduction band gets connected with conduction band, valence band gets connected with valence band, and there is no edge states. However, at the interface between a quantum spinel insulator and a trivial insulator, as I have already mentioned, that there is band inversion at the gamma point of a quantum spinel insulator. That means some portion of conduction band moves to valence band and some portion of valence band moves to conduction band. And at the interface, the valence band of trivial insulator gets connected with conduction band of quantum spinel insulator, and the conduction band of trivial insulator gets connected with valence band of a quantum spinel insulator. So as a result, there is a edge state, and these edge states are highly robust under non-magnetic impurities, and they are protected by time reversal symmetry for the case of quantum spin-Hall insulator, and they are helical. That means spin momentum locked. That means up spin electron will use 1s to go from source to drain, and down spin electron will use another s to travel from source to drain, and they are highly robust under non-magnetic impurities. And the origin can be described by employing bulk boundary correspondence principle. So now let's talk about the electronic band structure for armchair and zigzag is Bismuthene nanoribbon. So as you can see that the bands are doubly degenerate because of the existence of both time reversal and inversion symmetry. However, for pristine nanoribbon, there are non-trivial edge states due to dangling bond. Sorry, there are trivial edge states due to dangling bond along with non-trivial topologically protected edge states. That's why we can't see Dirac linear dispersion around the Fermi level for the case of pristine nanoribbon. However, if we passivated the edges of the nanoribbon by hydrogen passivation, so here the black circles represent the hydrogen, those trivial edge states due to dangling bonds are vanished, and we can observe the Dirac linear dispersion around the Fermi level. So this is the electronic band structure for armchair passivated armchair nanoribbon, and this is the electronic band structure for specified zigzag nanoribbon. So as you can see, if we specified the edges of the nanoribbon, the Dirac linear dispersion now arises around the Fermi level. So the existence of trivial edge states can be shown by plotting the band structure of pristine zigzag nanoribbon without SOC. So this is the band structure for pristine zigzag nanoribbon without SOC. So as you can see that without SOC, there is a state around the Fermi level. And these edge states correspond to the dangling bond states. However, if we specified the edges of the nanoribbon, those trivial edge states through dangling bond are vanished, and we can't see any edge states without spin orbit coupling for the case of a specified zigzag nanoribbon. We have also described the local density of state for the case of a specified and pristine zigzag nanoribbon. So as you can see that there are high local density of state at the edges of the nanoribbon. However, at the bulk of the nanoribbon, the density of state is almost zero, and the density of state at the edge, local density of state at the edge, is significantly higher for pristine zigzag nanoribbon due to the existence of trivial edge states due to dangling bond in comparison with a specified nanoribbon. And we have also analyzed the conductance versus energy for both pristine and specified nanoribbon under various vacancy concentration. So as you can see, even at 2.10% vacancy defect, the conductance remains at 2 at the bulk band gap. However, the bulk states are highly suppressed by vacancy defect. So this is the structure for our proposed device. This is a double gate device. So we need to apply different voltages to top gate and bottom gate to intentionally break the inversion symmetry. We assumed that the drain to source voltage varies linearly from drain to source, and VT and gate voltage induces a staggered sublattice potential to induce the inversion symmetry. And the electric field can be given by this formula. And we have used the hexagonal boron nitride in our insulating layer. And for hexagonal boron nitride, the thickness of hexagonal boron nitride is 1.73 angstrom, and the thickness of the nanoribbon is 1.73 angstrom, and thickness of hexagonal boron nitride is 3.17 angstrom. So here is the important part. When I will talk about the code, what I did is that I calculated an expression that how much gate voltage will drop in gate. Then I subtract that voltage and use that voltage in my NEGF equation to intentionally break the inversion symmetry. Now I have also showed the electronic band structure for a specified zigzag nanoribbon under an applied electric field of 1.17 electron volt, 1.17 volt per angstrom. So as you can see that as inversion symmetry is broken, the bands become non-degenerate. However, as time reversal symmetry is still intact, the energy of downward spin electron at K is equals to the energy of up spin electron at minus K. And due to topological phase transition, an energy gap opens of 0.23 electron volt at the electric field strength of 1.17 volt per angstrom. Then I have analyzed the transfer characteristic for both pristine and specified armchair and zigzag nanoribbon. So as you can see that as for pristine nanoribbon, there are trivial resistors to dangling point along with non-trivial topologically protected resistors. That's why they have a higher on current in comparison with a specified nanoribbon. Moreover, uh, the moreover, it requires significantly high voltage to switch off the pristine zigzag nanoribbon in comparison with a specified zigzag nanoribbon. So a specific zigzag nanoribbon is this color, this cross curve, and pristine zigzag is this circle line. So as you can see, by specifying this zigzag nanoribbon, we can reduce the threshold voltage. However, by specifying this nanoribbon has one drawbacks. It increases the subthreshold swing. Next, I have analyzed the impact of channel length. So as you can see that if we increase the channel length, then subthreshold swing reduces. And finally, I have also analyzed the transfer characteristic under various vacancy defect to show the robustness of my device. So the black curves represent the transfer characteristic for a specified zigzag nanoribbon under various vacancy concentration. So this curve remains constant even at 2% vacancy defect. However, for the case of pristine zigzag nanoribbon, because there are non-trivial resistors to dangling bond, the transfer characteristic deteriorates with increasing vacancy defect. Next, I have also calculated the important device parameter, for example, quantum capacitance, and then delay time, and then dynamic energy dissipation. So for calculating the total capacitance, I have assumed uh, I I have taken some approximation. So I calculated the capacitance. I calculated the insulator capacitance by using the capacitance of a simple equation of a parallel capacitor, and the quantum capacitance of the channel by employing this formula. This formula is from the equation of this formula is related that the quantum capacitance is related to the density of state, and I got this equation from the book of Professor Shubhra Datta, Atom to Transistor. So after calculating the total capacitance, I calculate the delay time and dynamic energy dissipation. And I have also compared my result with existing literature. And based on my work, I have published two papers, one in Physica Scripta and one in New Journal of Physics. I will also post the link of those two papers in the description box below. And if you get benefited from my code, please do consider cite my papers. Thank you, everyone. In the upcoming videos, I will try to somewhat explain the codes that I have written to simulate all those figures. So there might be some mistakes in my delivery. If you find any conceptual issues, please feel free to write those down in the comment box. Thank you for watching my videos. Thank you.